Up until now, everything we've talked about has been what in chemistry books we might call a pure substance. That means it's something that we could describe entirely by knowing its chemical formula. Right? So if I hand you a glass of water, a bottle of water, and I say this is water, you know everything about what's in it. Right? You don't have to ask me anything about what kind of water, or whether it's strong water or weak water or anything like that. The fact that it's water tells you all that you need to know about what the properties of that particular substance would be. Today, we're going to take up solutions, which will be an example of what is, in chemistry terms, known as a mixture, where we have two or more things put together. Okay, solutions are a particular subcategory of these. Solutions happen a lot in chemistry labs. They happen a lot in real life too, because gosh, there's all sorts of solutions flowing through your body, for example, that carry various nutrients to where they need to get, and things of that sort. So it's an important topic there. It's an important topic in, say, environmental chemistry, where there's lots of things dissolved in water in the water system. So to talk about the idea of pure substances and mixtures, we need a little bit of some vocabulary to do this, okay? Again, a pure substance is something that is described completely if you know its chemical formula, right? You know the chemical formula, you know everything about it. Fancy term for that, or a chemistry book term for that, is that that substance has a fixed composition. So when we say water is H2O, that means every single sample of water, no matter how large or small it is, where it came from, there's always 2 hydrogen atoms for every 1 oxygen atom. We could turn that into mass percentages if we wanted to, right? We've done that in an earlier video. And so that describes everything about it. If I have a mixture, that's a combination of 2 or more pure substances, right? So suppose I took a glass of water and I just dissolved some salt in it, right? Now I've got my salt and my water in there together, right? So I've got a couple of different substances. The mixture, once I go into that category, now it has a variable composition. So when I said I was going to make some salt water, I didn't specify whether I was going to take a little pinch of salt and throw it in there, or whether I was going to get out a measuring cup and put a cup of salt into my water. Okay, I'd get different solutions, right? Certainly if I had to taste it, I'd have a very different reaction depending on how much salt I had put in the water. I might not like any of them that much, but if I put a small enough amount of salt, then it wouldn't be overly nasty to have to drink, perhaps. Okay. So if I want to be able to describe a solution, I'm going to have to know the relative amounts of each component, right? There could be 2 components, like in the case of my salt water. There could be a whole bunch of components, like if I just, I don't know, went out and took a sample of some lake water someplace, I could probably find a lot of different substances in it. So when we talk about solutions, which is the kind of mixture that we will deal with primarily in our course, a solution is a homogeneous mixture. What that means is that if you take a scoop out of a solution, it doesn't matter if you sample it near the top or the bottom or on one side of the container or the other, you're going to get the same composition. Okay, so it's uniformly mixed. Anytime I take something and dissolve it in water, for example, if it's really dissolved, it should stay dispersed throughout, and I shouldn't have concentration gradients from the top to the bottom, say, of my container or anything like that. That's in contrast to what would happen if I took, I don't know, suppose I took 2 solids. Suppose I took some salt and I took some sugar and I just poured them on my countertop and I just mixed them around a little bit with my hands, right? If I took samples out of that in different places, I might at some points get something that was all or almost all salt. At other points, I might get all or nearly all sugar. And so my mixing is not uniform there. That's not a homogeneous mixture. Solutions often exist in liquid phase, and that's what we'll talk about primarily. There are certainly gas phase solutions. Air we could think about as a solution, right? We have nitrogen and oxygen and a lot of other things that are present in very small amounts, and we could treat that as a solution. It would work just fine because the air is certainly uniformly mixed. There also are solid solutions, which surprises some people. If you were to go into materials science and work with alloys, those can be treated as just solid solutions, because what happens essentially is you get, say, 2 metals to mix while they're in the liquid phase, and then you just cool it quickly. And then what you have is just you lock in where everything was. And so you can definitely treat a lot of different alloys as being solid solutions of the constituent metals. There's just a bit of terminology here, right, that says if we are talking about the solvent over here, so the solvent is the thing that there's a lot of. And obviously that's a fairly loose definition. In principle, there's no reason I couldn't have a solution where I had equal amounts of two components, and then I'd have a somewhat arbitrary choice, right? The solute is the stuff that is dissolved in the solvent. Okay, so the solute is the minor component or components. There could certainly be more than one solute. I could take my salt and my water and throw them, my salt and my sugar rather, and throw them both into the same water. Then I would have a solution in which both of those things were dissolved, because there's no reason why they couldn't both dissolve in the water. The solutions we'll talk about are primarily aqueous solutions. As it says down here, aqueous is a fancy word for water, right? Think of the root of aquatic, for example, right? That's where that's coming from. That says the solvent is water. Why are those the solutions we'll talk about? Because the world is full of water, after all, right? And so in chemistry happening out in the environment, in chemistry happening in your body, in a lot of important places, there's just a lot of different things that happen in aqueous solutions. And so that's why they're an important topic in a lot of chemistry courses. Those are my hands. So this is a picture that's actually in your textbook. It is a frame capture actually from me teaching a version of this class that actually used to play on the local PBS station a long time ago. So it's before HD TV, obviously, because it's not the best picture. But those are two different solutions of copper sulfate, right? CuSO4 here, that's the formula for copper sulfate. And I have two different flasks there. Each one of them has 100 milliliters of solution in them. The one on the left-hand side of the screen very clearly is a darker blue color, right? The one over here is much clearer looking. You have to have it sitting on that white piece of paper, mainly because that lets us see that there is a little bit of a blue tint to that solution, whereas this one we can see quite readily that it's got the blue to it, all right? A little bit of an aside here, the height of the liquid in the two different flasks is clearly not the same, right? And students often ask about that with regards to this picture. They really do both have 100 milliliters in there, very exactly, actually. What happens is those are what are called volumetric flasks, and they're for measuring volumes very accurately. And so each individual flask is actually calibrated separately. They blow the glass, put the bulb in the bottom there, and then there's basically a machine that injects exactly 100 milliliters of liquid in there. And then it comes and it puts the mark on the neck of the flask where the liquid rises up to. And so the fact that the liquid is higher up in this flask over here just means that this one must have a little bit more volume down in its rounded part for that, but they really are both 100 milliliters. What's different about them? The amount of copper sulfate. This one has about 4.5 grams of copper sulfate in it. This one has only about 0.5 gram, right? So there's a lot more copper sulfate in the solution over here. That's why it's got a darker color. We used copper sulfate for this because it has that nice blue color that makes it easy to see the difference in the concentrations there, right? So we would say that this solution over here is the concentrated solution. This one is the dilute solution because it has relatively less of the solute in it, or relatively more of the solvent. All right, so those are just a couple of examples of solutions. When we want to talk about our solutions, I've mentioned that we have to know the relative amounts of the two components. The word we use for that is we have to know something about the concentration of the solution. All right, that's going to be how we describe how much of each thing is there. The concentration unit that chemists like the best is actually going to be something known as molarity. And many of you will remember molarity from high school chemistry, perhaps not fondly, but that's okay. So this, the molarity word there, molarity is defined like it says here. So the definition says molarity is equal to moles of solute divided by liters of solution. All right, that's the official definition. That means it has units of moles per liter. We also write this with its own abbreviation. We use an uppercase M for molarity. So if you see that uppercase M as a unit, that's what it means, right? Lots of units, most units are case sensitive, right? So a lowercase m is a meter, for example, and an uppercase M for us is molarity. You can measure concentration other ways. We could just say what mass of each thing we had, or something like that. Why are chemists fond of molarity? Chemists are fond of molarity because we're fond of moles, right? And so chemists often want to know how many moles of something they're working with. And for solutions, measuring the volume is usually the easiest thing to do. right? If I pour my solution into anything, any kind of container that has just marks on it, I can use that to measure the volume. If I know the molarity and I know the volume, this says I could easily find the number of moles, right? Because that says molarity is equal to moles over liters. So if I rearrange that, I would get that molarity times liters is equal to moles. And so it's an easy route to moles. We don't usually talk about the mass of a solution, because if I weigh the solution, if I took my copper sulfate solutions from the previous slide and I weighed them, most of the mass in there is going to be from the water, because I have a lot more water than I do copper sulfate. All right, and so the mass difference between those two solutions would not be that large, right? And so it's usually better to talk about things in terms of other concentration units, and molarity is the one we will use, although there are certainly others that will pop up sometimes and that you might encounter if you end up in a field that does a lot of work with solutions. So I'm going to do a molarity calculation here, just a simple manipulation as an example for calculating the concentrations of solutions, okay? And I have the two solutions that were there before. I'm going to do the one on the top, I believe. So I'm going to do this one, and I will just tell you what the molarity is for the one on the bottom in case you care to do the calculation yourself to verify that, okay? Here's my stuff I know. I know molarity is moles of solute over liters of solution. Notice that officially it's liters of solution. So that says I don't want to measure out if I'm making 1 liter of solution. Well, if I'm making this 100 milliliters of solution, let's say, I don't start by measuring out 100 milliliters of water. I would start by measuring out the copper sulfate I want, putting it in the flask, and then I'd add some water, shake it up a lot so that it got nice and dissolved. Then I'd add more water, shake it up some more. And finally, I would top it off to the right volume and mix it up again, right? So I want the volume that I'm saying, the 100 milliliters is supposed to be the whole solution in this case. So to get here, I want to get to moles. And so I'm going to have to go from 4.57 grams of copper sulfate to moles, right? And I've got my conversion factor over here. I was kind and wrote myself the molar mass on my slide there. And I'm going to go from my 100 milliliters into liters, okay? You could do this either of a couple of ways. You could take the 4.57 grams and convert them to moles, take the 100 milliliters, convert it to liters. That's easy. And then you could divide the moles by the liters. I'm going to do it more in a concerted kind of calculation. So I'm going to say what I know about my solution is that it has 4.57 grams of copper sulfate. And that's in 100 milliliters of solution. Then I'm going to convert my milliliters to liters. I didn't write it down there, but a liter is 1,000 milliliters, right? Milli is 1,000th. I want to get rid of the milliliters, so that means I put 1,000 milliliters up here. I put 1 liter down there. Now I'm in grams per liter, but I don't want to be in grams per liter. I want to be in moles per liter. So my next task is to convert the grams to moles. That means I want to get rid of the grams. So my 159.6 grams of copper sulfate goes down here. My 1 mole of copper sulfate goes up here. Okay, then my milliliters will cancel, my grams of copper sulfate will cancel. I'm left with moles here and liters there, which is what I want. So then I just multiply. My notes tell me I get 0.286 molar for that. Is my concentration for that solution. I said I would tell you the other one. If you want to do the other one, my notes next to me here say that I should get 0.034 molar solution. That was for the one that had 0.54 grams of copper sulfate. So really everything in the calculation would be the same except for changing this number over here. And so there's not a whole lot of I guess, great stuff to be gained by doing the calculation. But if you want to just do one for practice, that would be the one that's at hand for us, okay? The other thing I'm going to talk about in this segment is the idea of dilution, okay? Dilution is a common lab procedure, and so if you were actually going into the chemistry lab this semester and doing lab experiments, you would end up doing a bunch of dilutions for things, okay? Dilution involves making a solution starting from a more concentrated solution. So you take the solution, you're going to essentially add solvent to it. In the case of aqueous solutions, that means you're going to end up increasing the amount of water that's in the solution for that. Why do we do that a lot? We do that a lot in large part for practical reasons. Like when in the chemistry labs in Heldenfels, for example, we go through very large amounts of certain reagents, things like hydrochloric acid, right? So we buy lots of solution of HCl. When we do that, we like to buy it in a very concentrated solution because, among other things, that reduces the weight and the volume, and it makes the shipping costs be less, right? Because we can take a small bottle of a very concentrated solution and make a lot of diluted solution. All right. And so when we buy that hydrochloric acid, for example, it comes in containers that it's something between 15 and 16 molar is the concentration, which is quite a lot, right? Oh, let me make a comment about molarity, and then I'll do the dilution part here. If I look at my molarities here, you'll see that for the darker solution, I got 0.286 molar, right? Most molarities you'll see are typically going to be fractions of 1 mole per liter or a mole per liter, something like that. Okay. For aqueous solutions in water, in a liter of water, there's about 55 moles. You can figure that out from the density if you want to. And so in any aqueous solution, generally, there's going to be a lot more water than there is the solvent. All right, and that's a fairly general sort of thing, right? So if I'm doing this, I'm going to have to know how to calculate how much solution I want to use, how much of the concentrated solution, how much water do I want to use to make the right amount at the right concentration for my dilute solution. So I'm going to do an example for this as well. Again, the way this semester is going to go, I guess you won't actually be doing this manipulation in the lab, but it's still a useful thing to know. Okay, so. Hypothetical lab procedure, again, involving copper sulfate. So that's the theme for this video, I guess. So we have a large bottle that has 0.25 molar copper sulfate solution. And for whatever experiment we're doing, we need 100 milliliters of 0.1 molar solution. So if that's our task, we need to know how much of that original solution do I want to measure out. And then I would just then add enough water to that to bring its volume up to the 100 milliliters, okay? So the process for this would look sort of like this. If you're not sure how to do this, let's just think about what we're doing. So I've got a container here that's going to eventually have my my solution in it, right? And first, I'm going to put in here some of my 0.25 molar solution. Then I'm going to add water. And when I'm done, this is my volume. What I want to have in here is I want 100 milliliters total, and I want it to be 0.1 molar. Okay. So the first thing I can say about this problem is the volume that I need better be less than 100 milliliters, right? Because I have to add water to it to lower the concentrations. That's the first thing I can say I know about the answer. If I get an answer that's bigger than 100 milliliters, then it's definitely wrong. All right. So if I'm doing this, the thing I have to realize is that the copper sulfate moles that are in this have to come from here, right? Because there's no copper sulfate in the added water. All right, so I need to get all the moles that belong in my 100 milliliters of 0.1 molar solution. They all have to come from the 0.25 molar solution that I'm dumping into my beaker. All right, and that's the trick, if you will, to solving this problem. Okay. This leads itself to a nice simple equation, which students like a lot. Students like this equation a little bit too much and often use it in situations where it doesn't apply, I'm afraid. And so let me just develop the equation here, and then we'll just go and use it from there. So I want to say the moles in the concentrated solution have to equal the moles in the dilute solution. Right. What I know is for the dilute solution over here, I know its molarity and its volume. Okay. Remember, molarity is moles over volume, over liters. Right. So that says if I multiply molarity times liters, I get moles. Okay. So that says where it says moles in the dilute solution, I can call that M times V, where V is volume and M is molarity. And on this side, that's got to be equal to M times V again. So the equation we end up with here is something like M1 V1 equals M2 V2, where the ones and twos represent the two different solutions, the concentrated one and the dilute solution, right? In this case, I know both things here, and I know the one thing over there, so I'm going to be good to solve. All right, so we'll solve the equation. solve the problem, then I'll give you sort of a cautionary note about that equation, because I often see students use that in places where it's just not a good idea. So this is my my overall statement of things, right? And the equation I'm going to use is the one I just found. So the first thing I'm going to say is the moles equal the moles, right? The moles in the two solutions, the moles of copper sulfate, have to be equal, okay? So that says I'm going to start with my M1V1 equal to M2V2. I'll call this thing M1, I guess, and I'll call this M2 and that one V2, all right? And then I'm just going to solve. I'm going to solve for V1 because that's the thing I don't know. That's equal to M2V2 over M1, which means in our case, it's equal to 0.1 molar. I'm just going to leave my volume here in milliliters because then I'll get my answer in milliliters. I could put that in as 0.1 liter and then my answer would come out in liters. As long as I'm paying attention and know what units I'm in, it doesn't make much difference. And if I do that and multiply that out, I have notes sitting next to me that say that comes out to be 40 milliliters. I probably didn't really need notes for that one, I guess. Just looking at the numbers there. Okay, so that says that I need 40 milliliters of my 0.25 molar solution. First of all, that's less than 100 milliliters. That checks off the first box. Second of all, I've reduced my concentration to less than half of what it was. And my 40 milliliters is a little bit less than half of the 100 milliliter volume. So it feels like I have things about right there, probably. Okay. If I look at this equation. This equation says the moles equal the moles, okay? So if you're ever about to use that equation, M1V1 equals M2V2, stop and ask yourself, are the two numbers of moles equal, okay? When I say students use this equation incorrectly or in bad places, typically that's when we're talking about two solutions actually reacting with one another. In that situation, the number of moles of the two things may not be the same. And in that case, if you solve with this equation, you're going to get the wrong answer because that equation says the moles equal the moles, right? And so as long as the two numbers of moles are equal, then that equation is terrific and it's simple. All you have to do is make sure you stack things up and you do the algebra correctly, right? So again, by writing my units in here, I sort of get my check on that because I see my molarities can go away and I come out in volume, and that makes me happy. All right, that's a quick run through of a couple of calculations involving molarity. We'll do some more things related to that in class coming up.